In the last videos, we have talked about topology optimization and how it can lead to designs beyond the state-of-the-art. We have also demonstrated on the application of Hall effect thrusters that within only 1 hour, topology optimization has led to an original design that respects 3 magnetic requirements at the same time. In this video, we will be showing the potential of topology optimization on the application of electric motors and in particular on the permanent magnet synchronous machine. If you are not familiar with this application, please go back to our first video where we briefly explained how it works. Now, let's start by defining a series structure of an electric motor for our illustration. In this structure, the magnets are drawn in yellow color, the coils are red, and all other blue areas represent ferromagnetic materials. Given the periodicity of the structure, we do not need to simulate the entire structure, but only 1/4 of it. This reduces the simulation time and speeds up the design process. This is a commonly used technique. Now, let's talk about the design problem of this type of electric motor. Indeed, there are a multitude of problems that we can solve by designing the magnetic structure. But in this video, we will focus on a single objective that is related to the magnetic field generated by the rotor magnets. So the first thing to do is to get rid of the coils. Here, we are interested in the magnetic field generated by the magnets along the central arc in the air gap. This arc is drawn in green. In this region, the magnetic field looks like the orange curve. It is known in the law of electromechanical energy conversion that the smoothness of the rotor movement is related to the smoothness of the magnetic field curve. Our objective is therefore to design the electromagnetic structure of the motor so that the radial component of B in the air gap comes as close as possible to a given smooth sinusoidal curve, shown here in blue. Now, let's mesh the structure and make the optimization work. For efficiency purposes, we are going to first use the symmetry of the structure in order to define the problem, or just the half of it. The other half will be defined automatically the same way. Here we have the possibility to design the whole structure, i.e. the magnets, the stator, and the rotor. But we are going to limit ourselves to only one part, which is the outer part of the rotor. That's why all the regions that will not be designed are drawn with a black outline, and only the variable region is going to be meshed. Here, every mesh of the exterior part of the rotor is a variable. We remind you that the purpose here is just to see the potential of topology optimization and not to have a solution to exploit. Let's go. As you can see, we start for now with a coarse mesh that we are going to refine afterwards. We recall that the blue color corresponds to meshes that are filled with ferromagnetic material, and the gray ones are void meshes. Here we show the changes that happen in each iteration during the design process. We show the obtained and the objective magnetic field, as well as their harmonic distortion, in order to quantify how far we are away from the objective. We can see that in a few iterations, we already begin to have an idea, and the whole process has taken only 18 minutes. We see that the solution still will have undesirable harmonics, but they are due to the shape of the stator. There's no way to compensate for this by the rotor design alone, and in order to have a more appropriate solution, we have to reintroduce the stator regions as variables. But having the perfect solution is not the purpose of this video. Let's leave now and try a finer mesh. Here, the process will require more iterations. In this example, it took 80 iterations to converge, costing 1 hour and 38 minutes of computing time. We can notice that the design becomes more complex and more organic when it is a finer mesh. And this is where the power of topology optimization lies. And in order to give an idea of what this could look like for an even finer mesh, we've decided to put directly the obtained solution. It is more organic and more complex, but it's a high-performance solution in respect of the objective. For feasibility or manufacturing issues of those solutions, they are included in post-processing stages. We have decided to not include them, but in order to have an idea about how it works, please go back to our previous video. Given these designs, we hope to have shown the interest of topology optimization. That's it. Thank you for watching.